In this lecture, we'll talk about planets and moons. We'll look in more detail at the characteristics of rocky planets and of gas giant planets. And we'll talk about how moons form around planets and what their properties are. All of this is with reference to the solar system, but with the expectation that we will be talking about these properties for exoplanets as well. What are the ingredients for a planet? We've seen that planets form from rocky material that gradually accretes to form larger and larger objects. The material that planets form from depends on their distance from the parent star, because the lighter material is being driven away by radiation from the young star, so that only the most massive cores in the outer solar system can accumulate large gassy envelopes. Meanwhile, what minerals form and persist in a planet depend also on the distance from the star, because beyond a certain temperature, liquids will turn to gas or vapor and be driven away, and even metals or rocks will be vaporized and driven away. So the material of a planet depends on its distance from the parent star. We can see this here. Hydrogen and helium are the dominant materials in any solar system, and the size of these boxes indicates their relative abundance in the forming solar system by mass. So 98% of the mass of a young solar system is hydrogen and helium. All the hydrogen compounds form about 1.5%, the rocky materials less than 0.5%, and the metallic material about 1/5%. So the stuff of planets is a tiny fraction of the mass of a forming solar system. And these materials have to persist at certain temperatures. At any temperature below about 1,000 to 1,500 Kelvin, metals can persist in the liquid or solid state. At a temperature below about 1,000 Kelvin, rocks are not vaporized or liquefied and so can exist in solid form. At a temperature of about 150 Kelvin, hydrogen compounds, including not just water but methane and ammonia, can exist either in solid or liquid form, but above that temperature they will be vaporized and probably driven away. This is the condensation curve that describes how different materials can be solid or liquid in terms of their distance from a star. The rocky material that forms planets in the inner solar system is not associated with a large amount of light gases because of the radiation from the young star. Radiation pressure drives away gas and also small dust particles from the inner regions of a solar system. So the remaining matter in the protoplanetary disk is primarily silicate rocks, iron, nickel, aluminum, and a very small amount of residual hydrogen and helium. As we've seen, these planets grow by the accretion process. Size matters for a planet because it dictates much of its subsequent properties and behaviors. Small rocky planets do not have sufficient mass to accumulate an atmosphere. Mercury is a good example in the inner solar system, and their physical size is such that internal pressure does not create liquid magma or a molten core. Therefore, they are not geologically active. Mercury is geologically dead. Mars defines the boundary on a planet between something that is geologically active and not geologically active. We know that Mars has been geologically active in the past, has the largest volcano in the solar system, for example, but is not very active at the moment. The Earth and Venus, very similar in size and both quite a lot larger than Mars, are both massive enough to have sustained active geology throughout their entire histories. And the Earth, we know, is a currently active geological planet. This also relates to the surface material or the surface properties. A low-mass planet with no atmosphere will be peppered with impacts from space, and so its surface will show a cratering history of debris in the solar system. And we actually use this information to talk about the history of cratering in the solar system and what happened to all the debris left over from planet formation. Whereas a planet with sufficient mass to attract an atmosphere is shielded from cratering. The meteors and impactors burn up in the atmosphere, or there's liquid on the surface causing erosion to eradicate evidence of craters. And so we cannot see the cratering history of the solar system from such planets. The large rocky planets are geologically active, and that also means that their surfaces are formed and reformed periodically. If you go outside on the Earth's surface, wherever you live, and pick up a rock, it's unlikely to be more than a few 100 million years old. And that's a small fraction of the age of the Earth at 4.5 billion years. And that's because erosion on the Earth's surface and resurfacing caused by tectonic activity and volcanism continually changes the surface of the Earth, reforms and forms it. And that's true of all planets like the Earth, Venus another good example. The other thing that happens is a magnetic field. Small objects are unlikely to have sufficient metallic core to form a magnetic field. The Moon, because of its particular history, we know to have no magnetic field. But the magnetic field, for example, of Mercury is also weak. Magnetic field in a terrestrial planet also plays a role in its properties, because the magnetic field acts as a shield to protect a planet from violent solar radiation and intense ultraviolet radiation. So, magnetic fields shield a planet from harmful rays from space and also indirectly help a planet retain its atmosphere. Even a planet with a thick atmosphere is slowly losing that atmosphere into space, as molecules at the upper edge of the atmosphere slowly gain sufficient average velocity to leak into space. This is a slow process, and the terrestrial planet may take hundreds of millions of years to leak its atmosphere into space. The other thing that determines the properties of a planet are, of course, its distance from the Sun or its parent star. For identical planets at different distances from the star, we see different effects. The distance of a planet from a star or the Sun affects its properties significantly too. If we look at the difference in properties of identical planets, varying only in their distance from the Sun or a similar star, we can see significant differences. A planet like the Earth, for example, situated much closer to the Sun, would be high enough temperature that it would be unlikely to retain an atmosphere for long, and it would be impossible for liquid water to exist on its surface. If it was sufficiently close to the star, it would be tidally locked, where the gravitational interaction with the star caused one surface to always face the star, much as the Moon is tidally locked to the Earth and we always see its one same face. At a larger distance, the temperature can be right for liquids to form and persist, and for the atmosphere to be retained. That is the essence of a habitable zone. The same planet at a much larger distance from the star is, of course, colder, and that colder planet would be unlikely to have any liquid. So these are, although it may have liquid under the surface, kept liquid by pressure and radioactive heating from the rocky material. So we can expect to see all of these variations in planet properties in the exoplanet systems we are now discovering out in space. What about gas giant planets? They form outside the frost line, where the dominant matter in the debris disk is hydrogen and helium gas and associated ices from compounds involving hydrogen. We need to talk about how astronomers define the word ices. Most of the material in a young solar system, or in the Sun itself, is hydrogen and helium. And the disk that forms around the star is also mostly hydrogen and helium. Helium is inert and doesn't form compounds, so it is essentially remote from the processes of molecular clouds, molecular formation, and the formation of rocks and ices. The ices in the outer solar system are mostly frozen hydrogen compounds. Water vapor, and ice particles are the dominant one, but also frozen methane, ammonia, and frozen carbon dioxide, or dry ice. And we see different amounts of these different ingredients in outer solar system bodies. Gas giants have a different composition and structure from rocky planets. They have much stronger gravity, of course, which compresses the gas and differentiates it in a way that we never see in the inner solar system. The compression leads to a large amount of heat, with the temperature steadily increasing towards the center. When infrared observations were first made of Jupiter 30 years ago, they showed that the infrared radiation from Jupiter was larger than the amount expected given its distance from the Sun. In other words, there was an extra source of heat in Jupiter, which we now attribute to its very slowly contracting and releasing heat into space. This large amount of compression and pressure creates quite high temperatures inside Jupiter and Saturn and the other gas giants, despite their large distances from the Sun. There is no place on Earth that reaches the very high pressure typical of these gas giant planets, caused by the extreme weight of their outer atmospheres pressing down. This is a temperature profile of what we might typically see in a gas giant like Jupiter or Saturn. Below the visible clouds at the top surface, the atmosphere grows hotter as it becomes compressed, resembling a hot, thick fluid. But in the lower levels of the atmosphere, the pressure is so great that matter actually forms an exotic state of matter called a supercritical fluid, which is a boundary condition between a liquid and a gas. Deeper still, the gases become so compressed that they take on the properties of a solid. And this is the situation where we can have metallic hydrogen, a substance essentially unknown on the Earth. The surface, where the rocky core exists, is likely to be a bizarre mixture of ice, rock, and metallic hydrogen at pressures of hundreds or thousands of atmospheres. What about moons? How do they form, and what can we learn about their properties? Essentially, moons form in miniature versions of the formation of the solar system itself. They form alongside planets in miniature debris disks or by collisions. They also form by accretion, the same way the planets in the solar system form. So we can imagine the moons of the giant planets in particular, each of which has dozens of moons, being formed in a scaled-down version of the formation of the solar system itself. The planetesimals can also be pulled into orbit, so moons can also form by sweeping up material from slightly further away over time in the debris disk that formed around the Sun itself. We have no example yet of an exomoon, which is a moon around an extrasolar planet or exoplanet. And that's just because exomoons are so small and so low mass that instrumental techniques are not sufficiently sensitive to allow their detection. But we can speculate, as planets are a natural byproduct of star formation, and moons are a natural byproduct of planet formation, then in the extrasolar systems we've found, there will be exomoons. We just don't know how to find them yet. Several searches are underway. Looking at our solar system, we might conclude that moons are common. Mercury and Venus have no moons, but the other planets do have moons. One large moon for the Earth, 2 small moons for Mars, and dozens of moons for the giant planets. This graphic shows the relative sizes of the moons and shows that in some cases, the largest moons rival the size of the smallest planets. Remember that Pluto has been demoted to the status of a dwarf planet. But even compared to Mercury, we have Galilean moon of Jupiter, Ganymede, and the largest moon of Saturn, Titan, which rival Mercury in size. So there's no strict demarcation based on size or mass between a moon and a planet. We think of moons as being dead worlds, framed in large part by experience of the moon. Earth's moon appears to be geologically dead, has no atmosphere, surface is littered by craters, and we don't imagine it of a place with life. And yet recent observations have shown that there's a substantial amount of ice under the lunar surface, and there are possibly small isolated places where there might be liquid water under the surface. So the moon's not quite as boring as we thought it was. Many of the moons in our own solar system are quite interesting. They are distinctive worlds in their own right. And so in the context of astrobiology, where we're thinking of life in the universe and places where biology should exist, we can't rule out moons as being interesting targets for our investigations. Some of the moons have atmospheres. Titan, for example, has an atmosphere made of the same substance that you're breathing right now, nitrogen, and an atmosphere as thick as the Earth. Some have geological activity, others are heated by tidal effects, and so they have a lot of chemical dynamic processes going on in their surfaces and interiors. And they also have radioactivity in their cores that acts as a heating source, even when they're far from the Sun. So moons represent another category of objects that could potentially host extraterrestrial life. To summarize this lecture, we've looked at rocky planets, those that form inside the frost line of a protoplanetary disk. There's not much gas inside the frost line, so these are just rocky objects formed by accretion that attracts slender atmospheres. They have differentiation, which concentrates the heavy materials near the center. And they also, if they're of sufficient size, have geological activity that continually forms and reforms their surfaces. Beyond the frost line, we have the gas giant planets. They also have rocky cores, but they've attracted clouds of hydrogen and helium that dominate their mass. Pressure within these atmospheres creates bizarre conditions and extremely high pressures and temperatures unfamiliar on the Earth. We do not imagine these as being habitable locations in our solar system or elsewhere. However, moons are interesting in the context of astrobiology, because in our solar system there are moons with very distinctive properties, with internal energy, with atmospheres, and with chemically dynamical processes. We know there are moons with subsurface oceans, and so moons form a potentially interesting extension of the habitable real estate in the universe.